Well, we are very happy to have Tatevik Vardanyan who's a PhD student at University of Cologne, who will be telling us about quantum gravitational corrections in a closed universe.
Okay, yeah, thank you very much for the introduction. Yeah, so as you can see, the title is a bit abstract. You can't really tell what I mean about corrections to what. So I think at this point, I'll just start from my overview, and on the way you will understand what exactly we are going to calculate. Okay, so let me briefly give you some overview. So first, I'll try to give a brief introduction about quantum gravity. As you might know already, there are different approaches to quantize gravity. So particularly in my work and in our group, we are studying canonical quantum gravity. So I'll talk in detail about canonical quantum gravity. Then I will explain the application of canonical quantum gravity to the universe as a whole, which is called as quantum cosmology. So this first part is very general. And after that, I'll start motivating my topic, what exactly I'm calculating. So this canonical quantum gravity leads to the Wheeler-David equation, as I'll explain on the way. To study this Wheeler-David equation, we apply semi-classical approximation. And after that approximation, we calculate this corrected and uncorrected power spectrum. And at the end, we discuss also the possibilities to compare this with observations and whether we can hope to be able to observe this canonical, or it doesn't matter, just quantum gravitational corrections to the power spectrum. Okay, so what are the main motivations of quantizing gravity? First of all, you can find many details in Professor Kiefer's book, who is my supervisor. So yeah, I'm just giving main points, and if you are interested, you are welcome to look into that for more details. Okay, so one of the main reasons and motivations is first the Hawking-Penrose singularity theorems, which state that singularities are inevitable in general relativity. Therefore, general relativity is not able to fundamentally describe gravity, because at singularities we cannot understand the behavior of the matter, and one hopes that quantum gravity, which will be more fundamental theory, can help us to understand what is happening inside the singularities, or even avoid the singularities. So the next motivation is the unification of the four forces of nature. So as you know that the other three forces are well described within quantum field theory, and gravity is the only classically described force. So it is natural to assume that we can also quantize gravity so that we will have full quantum theory to describe all the four forces of nature. The third main motivation to quantize gravity is the problem of time. So as you know, in GR, general relativity, the time is dynamic. So we have dynamical space-time. But in quantum field theory, or just quantum mechanics, we have absolute space and time, and the matter lives in that space and time. And time is absolute and external variable. So as you can see, this quantum nature, in quantum theory, we have this absolute time. In GR, we have dynamic time. So we cannot really kind of unify these two different notions of time. So, which is why one can assume that if you go beyond and create quantum gravity, perhaps we can come up with a new notion of time, which will somehow unify these two different concepts. The quantum gravitational effects are expected to be observed at very high energies, or play a role at very high energies or very small scales. Those are called Planck scales. As you can see, those are extremely high energies, and it's basically impossible to reach to these energies in our accelerators. So the places where we can look for these effects then will be the early universe or the black holes. So this power spectrum that I'm going to discuss later on is exactly the CMB power spectrum. So we have this very early universe stage where we have very high energies. That's why we are hoping that quantum gravitational effects can be visible in this region. Now, as I mentioned, there are different approaches to quantize gravity. So I'll mention the general, let's say, branches. So the first is covariant quantization. So there are different methods within this. So through perturbation theory, effective field theories, renormalization, group approaches, and path integral methods. Next is canonical quantization. This is based on the Hamiltonian formalism, and this is exactly what I am studying. And the final approach is the string theory, where actually we have unifying quantum framework for all interactions. And quantum gravity comes as an emergent phenomenon from this string theory. Okay, as I mentioned, because I'm working with canonical quantum gravity, from now on, I'll only talk about canonical quantum gravity. So now let me explain how is the formalism built. So to start with canonical quantization, first we have to build Hamiltonian formulation of GR. So as you know, in GR we have the concept of space-time. But to be able to quantize it, we need to have a concept of canonical coordinates, some form, and canonical momentum, and then take them as operators. To be able to do that, we first have to foliate the space-time into three-dimensional space-like hypersurfaces here. And the evolution of this, so from one hypersurface to the other, you can describe the flow of time with this vector T mu. Now, if you decompose this T mu into tangential and normal vectors, we can denote this as n times n mu. N mu is the normal vector, and n mu is called shift vector. So in this, this n is called Leib's function. This Leib's function describes the temporal evolution of this hypersurface, and n mu, the shift vector, describes the spatial evolution of the hypersurface. As you can see, of course, I'm missing all the steps calculations. After this decomposition, one can see that the form metric can be decomposed into this form, where the shift vector and Leib's function are entering, and also HAP, which is the induced tree metric on each hypersurface. Okay, so basically we decomposed our manifold into this topological form. We have R times this hypersurface. Okay, now we start, of course, with Einstein-Hilbert action. So in the general form is given by this. So you also have the integration over the boundary term. And Einstein himself has already pointed out, I think in 1916, that this term is needed to have consistent variational principle. So it's not going to alter the Einstein's equations. So now our goal is to rewrite the Einstein-Hilbert action in terms of this conjugate momentum and conjugate coordinates, as I pointed out. As a conjugate coordinate, we are going to choose the HAP tree metric on this hypersurface. Now we have to also have some momentum. And it turns out that this KAB tensor, which is called extrinsic curvature, plays that role. So after some calculations, one can rewrite the Einstein-Hilbert action in this way. Here, entering here, so as you can see, first we have this Leib's function. This GABCD is called David metric, and it has the following form. This extrinsic curvature is defined like this. Also, we have introduced here the Ricci scalar on the hypersurface denoted by this. and it is related to the Ricci scalar of this space-time through this relation. I'm sorry. Now, after doing this, we can obtain the total Hamiltonian, which is given by this form. As you can see, it is composed of these two terms. First one multiplied by the Leibniz function, and the second one multiplied by the shift vector. And the total Hamiltonian density is, of course, related to the Lagrangian density like this, where HAB, as I said, is canonical coordinate, and PAB is its momentum. And as I pointed out, it is related to this extrinsic curvature like this. And we can write now our action in terms of this kind of using this Hamiltonian form. And taking the variation with respect to Leibniz function and shift vector will yield to the following constraints. So yeah, so this first constraint follows from the variation with respect to the Leibniz function, as you see, and the other one with respect to the shift vector. And the first one is called Hamiltonian constraint, and second one is known as diffeomorphism constraint. Okay, so the next step will be to quantize the system, right? And we have to take our coordinate and a momentum as operators and act on the wave functional. Now let us discuss the configurational space of the wave function based on which it's going to act. Okay, now the configuration space of quantum gravity is called superspace. So as I said, we are taking our coordinate as the metric, 3 metric. So it's basically the space of all Riemannian 3 metrics given on a manifold sigma. So we take a manifold and we are considering all possible 3 metrics on this manifold. But also because you can do some transformations and basically describe the same metric, but with respect to other coordinates. So to be able to make sure that all these metrics are independent, we are taking out this diffeomorphism part, which means that those are just mapping the same thing with in terms of just other coordinates. So now in this picture, we can see more clearly what I'm talking about. So maybe start with this. As I said, we first foliate the space-time into hypersurfaces, and then we see the temporal evolution of this hypersurface and the history of it. So you can see we start with the hypersurface and it evolves through time. So we recover space-time after this foliation, basically. So there is one-to-one correspondence. We are not losing anything after this foliation. Now, these superspaces, as I said, are the just combination of all possible 3 metrics. So it is in general infinite dimensional, but we can see later that because of the cosmological principle restrictions, we can get finite dimensional superspace, which is called mini superspace, which is only valid for cosmology. Yeah, also, now to understand what happens when we quantize the system. So in classical GR, you can see that there is a causal path from one hypersurface to the other one. But when you quantize the system, and because let's say each metric has some probability of existing, let's say, this picture becomes kind of fuzzy. So this is classically valid. So which means if you quantize it, for example, at this value of t, you should have all possible different metrics here. For example, A prime and etc. Yeah, I hope it's clear. Okay. Now, as I said, to quantize, we have to take our canonical variables as operators acting on the wave functional, which is functional of this metric, tree metric, as I mentioned. Yeah, so the same form as we have in quantum mechanics is applied here. And based on the procedure of quantizing the constraints, which is already developed by Dirac, and this actually can be done also in usual quantum mechanics. So it's not just typical to quantum gravity. We basically, the procedure dictates that we have to take our constraints that we obtained, apply it on the wave functional, and demand that it should be vanishing. So the first equation is called Villa-David equation. And second equation is called quantum diffeomorphism equation. Okay. Also, one more important thing that we have to already notice that in these forms, there is no notion of time. So the variability is missing. So this is the result of reparameterization invariance of the GR. But then later we can see that if we apply semi-classical approximation, in that limit, we can recover the notion of time. Okay, because particularly in my case, in my problem that I'm going to discuss, I'm dealing with cosmology. So in general, because this superspace is infinite, it's of course it's very difficult to deal with. And applying some restrictions, we can get a finite dimensional mini superspace called mini superspace. And the restriction that we apply is because we observe that our universe in large scales is homogeneous and isotropic, we demand that our metric and all these three metric, the hypersurfaces should look like this, which is known as Robertson-Walker metric. So we basically narrow down all the possibilities and demand that all Hij should look like this. Or if we lose the restriction, so this is based on homogeneity and isotropy. But if we only demand homogeneity, you can have more general Bianchi type metric. As you can see here, not only the scale factor enters, but also there is this another degree of freedom, which describes the anisotropies. Okay, so as I said, because these quantum gravitational effects are significant only at very high energies, this kind of energies have been present in the early universe. This is the main history of the universe that is believed in current science. Okay, so maybe I just missed this inflation part at the moment. I don't want to talk about this, but this cosmic microwave background that originated when the universe was 380,000 years old. From the Planck data, you can see that this power spectrum, these temperatures have tiny anisotropies in them. And we can see this map now, and we can observe it. So how did this originate? So starting with Big Bang nucleosynthesis. So first, universe started expanding. Then we have this nucleosynthesis, and after which, when the expansion continues, the universe cools down, after which the formation of first hydrogen atom becomes possible. But because there are photons at very high energies, they can always ionize the atoms. And when it cools down sufficiently, these photons are not able to ionize the atoms. So this phase is called now recombination, where the atoms are formed and these photons decouple from these atoms. And they, because of they don't properly scatter on the matter, until now we can observe these photons. And these photons are kind of a screenshot of the situation at the early universe. And you can see there inhomogeneities here already. And these inhomogeneities later grew to become these structures that we see, for example, galaxies. But now the question is, where does these inhomogeneities come from? One possible and very successful theory is the inflation. That universe started with inflaton field, which is a scalar field. It expanded the universe exponentially. I'll explain that there are certain problems in standard model that inflation was introduced to explain. But in addition to that, it has been shown that the quantum fluctuations of the inflationary field can become the source of this anisotropy that we see in CMB spectrum. So now the idea is to start with the inflationary field, quantize it, and also include the quantum gravitational corrections, and then see the spectrum that we measure now, is it possible to prove that these anisotropies, that there is in addition quantum gravitational corrections. So this is the main idea. I hope you could follow. Now, as I said, there are certain problems in standard cosmology, and also let me give the main ideas of the standard cosmology before moving to the problems. So, as I said, it is assumed that the universe is homogeneous and isotropic based on observations, and this is called cosmological principle. And this type of universe is described by this metric, FLRW metric. Written like this. As you can see, there is no shift vector entering because of the spatial homogeneity. So there is only Leib's function here. And the only dynamical variable is the AT, which is the scale factor. Now, I should also point out that this parameter called curvature parameter, it takes the value 0, -1, +1. So for k equals 0, it corresponds to the flat universe. -1 is the open universe where you have the hyperbolic shape. And for the +1, it's a closed finite universe. And this is exactly what I'm going to discuss, and I'll motivate later why I consider closed universe. Now, using this metric in Einstein equation, we will obtain the Friedman equations, which describe our space-time, our universe. So, yeah, we get these two equations. H is called Hubble parameter. So as you can see, there is this rho and P, which are the density and the pressure of the matter that is present in the universe. So the idea of Einstein theory was that the matter content affects the geometry. So in addition, in general, we also have to have this cosmological constant, which is also observationally favored that it should be there. Of course, the meaning of it is still debatable. In addition to this, we also obtain this continuity equation, which follows from this energy momentum tensor. But actually, these three equations are not independent, so you can derive this from these Friedman equations. So to be able to solve this, we need one more equation. So we can use the equation of state, which relates the pressure and density, and is related by this barotropic index. This barotropic index takes different values depending on the matter that we are considering. For dust, radiation, and for example, cosmological constant, we have these different values. And throughout the history, you know that we have radiation-dominated phase, matter-dominated phase, and is going to cosmological constant-dominated phase. So those are cosmologically relevant cases that we must discuss. So so having these values and substituting this relation into the Friedman equation, we can solve and obtain the relation for the scale factor. As we can see, when we have cosmological constant domination. For example, we have exponential expansion of the universe. Okay, now, so all this very nicely explains a lot of things in our universe, but there are some shortcomings. So there are following two problems in standard cosmology. The first one is known as a flatness problem. As you know, from Planck data and other data also available in cosmology, the universe is very, very close to flatness. And the question is why? If you look at this equation where omega is a dimensionless density parameter, which also contains all the components of the matter present in universe. So depending on the matter content, you get this relation, and the right-hand side is entering the curvature. So when k is exactly equal to 0, omega is exactly equal to 1. But the problem is, if you start with even a slight curvature, it will not evolve to become more flat. It will be the opposite. But now, if to have exactly k equal to 0, initially it demands some fine tuning. So we are more inclined to find a dynamical process that will lead us to the flatness instead of just fixing k equal to exactly 0 since the beginning or very close to 0. So this is known as flatness problem. Also, I should point out this AH-1 is called co-moving Hubble radius because we are going to use this later. The next problem is horizon problem. So if we define the co-moving horizon or particle horizon, which is the maximum distance that light can travel from time equal to 0, for example, to time equal to t, is defined like this. We can see that throughout the evolution, this horizon becomes larger and larger. And now that all this that is entering in our horizon was not causally connected before, but we can see that in CMB spectrum, it's homogeneous and isotropic. But the question is, how could it be homogeneous and isotropic if there are no causal connection? Of course, you can again fix it as an initial condition, but it is not natural. So the question is it possible to have a dynamical process that can lead to that kind of scenario instead of assuming it as initially given situation? And all these two problems that arise are because of this decrease of this co-moving Hubble radius. So to be able to increase of the Hubble radius. Now, to be able to explain or get rid of these problems, we can demand that there have been a phase when this co-moving horizon was decreasing, which is equivalent to the accelerated expansion of the universe. And also from the Friedman equations, you can see that the following conditions should be satisfied by the pressure and the density of the matter that can drive the universe to accelerated expansion to make sure that these conditions are satisfied. So theoreticians took a scalar field called inflaton. So the relations, the density and the pressure of the scalar field are given by this. So many details about the inflationary phase you can find in this nice book called Primordial Cosmology. Again, I'm giving only brief information. So now taking this scalar field as a matter content in the universe, if the Friedman equations take this form. And this scalar field is, of course, you know, described by the Klein-Gordon equation. Now, to have this, to be able to satisfy these conditions, we have to demand that this P, for example, so we see that P should be negative. So we have to demand that P is negative, which means in this case that potential energy dominates the kinetic energy. That is the condition that this scalar field should satisfy to be able to drive the universe to that kind of accelerated expansion. So the well-known and also observationally valid approximation is called slow roll approximation. So as I said, we have to demand that the kinetic term is much smaller than the potential term. And this one also follows from this, which means that we have expansion of the universe when the potential energy dominates, and it ends when the kinetic energy becomes also significant. So this is the main idea. Now to describe now these equations of motion that we had, which means the Friedman equations, because of the smallness of this term, we can introduce new variables, epsilon and delta, called slow roll parameters. And we can rewrite the Friedman equations in terms of these slow roll parameters. And also, just note that I define P and Planck as 3 pi over 2 g square root. Okay, now, why exactly I'm considering to the closed model of the universe? As I mentioned, the universe is very close to flatness at the moment, right? So then the question is, then why consider a closed model of the universe? Okay, so first, from the Planck data itself, if you check the data, you can see that it doesn't completely rule out the possibility of having a slight curvature nowadays. Also, there is a very nice paper and also currently discussed topic is that this interpretation of this Planck data is not straightforward, and actually these authors, where they publish their paper in Nature, they actually indicate that Planck data itself favors the specially closed universe by 99%. And because there are some tensions in this data, they claim that this positive curvature explains the anomalous lensing amplitude, and it also removes the tension within the Planck data set concerning the values of cosmological parameters derived at different angular scales. So it is not clear that it should be exactly flat, the universe. Also, if you look at the Planck data, there is lack of amplitude in this region, which correspond to the large scales, where closed model of the universe, if we have a closed model of the universe, because of the finiteness, we actually can show that indeed this can provide this suppression and low amplitude of the spectrum. This is exactly what I calculated and showed that yes, this is the case, and closed model can explain this low amplitude in here. And also, as I pointed out, even from the inflation, of course, if you have read about inflation, in most of the literature, they're starting with exact flatness, and they claim that these curvature terms are kind of negligible. But the point is, because as I said, we want to provide within inflationary phase that even if we had a slight curvature, the inflationary dynamics will drive the universe to the flatness. So it is even more natural to start with a curvature instead of exact flat universe. And of course, one more motivation I could give is this mathematically and philosophically, how are we accepting the idea of infinities in physics? Because the finite universe, the closed universe, is the only model that gives this finiteness of the universe. So there is also this interesting philosophical debate whether our universe should be finite or infinite. Okay, I hope I convinced you why this is important to discuss closed universe. Now, so previously I already explained you the main formulation of this canonical quantum gravity and where we have to start, what are the steps. So let me just quickly go through that so that to refresh your memory so that you can follow the rest of the talk. So we first foliated our line element given by this. So we have this Leibs and shift entering and also the 3 metric. Then we obtain these 2 constraints known as Hamiltonian and diffeomorphism constraints. And to quantize them, we take them as operators, act on the wave functional, and we obtain Wheeler-David equation and quantum diffeomorphism constraint. Yeah, so we basically have to follow the same steps, but in addition, because so here, as you can see, there is written G. So this is only coming from the variation of this Einstein-Hilbert action. So if we have a matter, so the total action is equal to Einstein-Hilbert action plus the matter part, right? So because we are considering inflation, we have to have Einstein-Hilbert action plus the action of the scalar field in general. Then you can see that instead of only G, you can also get plus this matter part, and the constraint becomes this plus matter part goes to 0, and same happens here. Yeah, and then I'll say more details on the way. Okay, so because we are discussing inflationary Feldman universe, as I pointed out, we are using this line element, and the shift is missing because of the symmetry. So the only dynamical variable is the scale factor. Okay, so the first step was to calculate the Hamiltonian, right? So as I pointed out, in this case, if you start with the total action, matter plus Einstein-Hilbert, you will get the contribution from both. So you can see you have also the momentum of the field entering here. So this comes from GR, these 2 parts, and this part follows from the existence of the matter content. So it's equal to Hg, let's say, plus H scalar field. And these momentum are defined like this. And also we introduce new variable alpha, which is equal to logarithm A over A0. Yeah. Now, because as I said that it is assumed that this CMB anisotropies can be originated from quantum fluctuations of the inflationary field, we also have to add perturbations to this Hamiltonian or to the field. So we have to take our metric, which we had, and also add some perturbations, which we later will quantize. So this part has already been done by Halliwell and Hawking in 1985. And they showed that if you take this, you can obtain the total Hamiltonian with this form. So it is composed of the background Hamiltonian plus the perturbation part. This perturbation part itself is composed of scalar vector and tensor parts. But because we are interested in this temperature anisotropies, which is related to scalar perturbations, we will not consider these 2 contributions, but we'll only concentrate on this. And these calculations of this total Hamiltonian also give this first order Hamiltonian constraints. Those are also obtained. And those are corresponding, the first one is linearized energy constraint, and the second and third one are scalar and vector parts of linearized momentum constraints. Now, I have to point out that if you have these arbitrary perturbations added up, in general, you don't have gauge invariance. So you have to properly take care of the gauge invariance so that we deal with only physical quantities. This form that has been obtained by Halliwell and Hawking is not gauge invariant, this perturbation part. So one has to obtain the gauge invariant perturbation Hamiltonians before moving on to quantize it. Okay, this so in flat case, actually, this was done by Mukhanov, and actually to obtain gauge invariant variable, you can add the perturbations of the scalar field and the perturbations of the metric, and you can, by combining this, you can obtain a gauge invariant variable. And actually, he expanded the action and then gathered these terms by hand and introduced this variable called Mukhanov-Sasaki variable. But there is actually a more, let's say, a more straightforward way to do that, which was introduced in a paper by David Langlois, where he actually applied this for the closed case, and he calculated this gauge invariant variable and gauge invariant Hamiltonian form that was obtained by Halliwell and Hawking. So as I said, there is this one option to do it by hand. The other option is to use this Hamilton-Jacobi theory and apply this to Hamiltonian systems with a set of first-class constraints, which is exactly what we have. We had the Hamiltonian and we had these constraints, first-class constraints. So it has been shown that if you solve, so if, for example, we have m first-class constraints, if we solve a equation, which is Hamilton-Jacobi-like equation, and you have this generating function S, solving this, we can obtain this new variables called QA and its conjugate momentum, which are gauge invariant. And those, and it is given by this related to the generating function, and also the old variables that we have, which are not gauge invariant, are related to the S generating function also as follows. And after solving this and obtaining the solution, you can show that gauge invariant Hamiltonian will be determined like this. So it consists of our initial Hamiltonian, which is not gauge invariant, plus this Poisson bracket. So if you sum these two, you'll get this gauge invariant Hamiltonian described by this physical gauge invariant quantity. Okay, as I mentioned, this has been done already by David Langlois in 1994, and he obtained the gauge invariant perturbation Hamiltonian that was derived by Halliwell and Hawking. And this is the form that he obtained. So Qn is the gauge invariant variable and Pn is its conjugate momentum. And Un alpha phi and Wn alpha phi are some lengthy functions of this kind of scale factor and the field. So I tried to continue quantization with this form, but it became very, very complicated and messy. So I did perform this canonical transformation where I introduced new variables, which are related to this Langlois variables like this. And we can get this very compact form for the new Hamiltonian, and we can continue our work with this. So here, actually, everything is given by cosmic time. By setting n equal to a, you can rewrite the Hamiltonian in terms of conformal time. And it was much more easier and straightforward to work with this form than continue with cosmic time and this. So yeah, this omega n square eta is a new function that is introduced and is related to these functions Wn and Un as follows. Now, to see whether we are in a right path, we have to take the large wavelength limit, which means a limit where this curvature will be insignificant. Therefore, we must be able to recover the result for the flat case. And indeed, we can show that if we take this large wavelength limit, we will obtain the exact form that Mukhanov and Sasaki had obtained. And this Vn tilde then becomes the Mukhanov-Sasaki variable. Okay, so now we have some gauge invariant variable to work with, which was this Vn tilde. But to be able, because our final goal is to relate this power spectrum that we obtain right after the inflation. So it has to evolve, right? The universe evolves, then recombination occurs, after which only we have this temperature anisotropy. So we have to relate the power spectrum at the end of inflation to the power spectrum of temperature anisotropies. To do that, we have to introduce one more variable called curvature perturbations, and these temperature anisotropies are related to this variable. So now the point is, and to be able to obtain the power spectrum in terms of this variable, which is called curvature perturbation, we have to relate these two variables, the one that we had, the gauge invariant variable, and these curvature perturbations. And after a lengthy but straightforward calculation, one can show that this following form is obtained. This phi n is called Bardeen potential. Again, the details of this you can also find in Peter Uzan book. Yeah, so the goal is, after calculation of the power spectrum, because of this relation, we can directly also obtain the power spectrum in terms of these curvature perturbations. Also, this another variable, theta, is actually used for the flat case, but it is not conserved quantity in the closed case, which is why we are working with this variable instead of this. But again, with the larger wavelength limit, you again have can relate these two variables. Okay, now after all this preparation, we are ready to quantize our system. As I said, for the inflation, we are going to use this slow roll approximation, and we demand that the scalar, that the kinetic term, kinetic potential must be much smaller than the potential energy. And we can rewrite this Hamiltonian. So the total Hamiltonian was equal to the background part plus perturbation part. So this can be, using these conditions, can we rewrite in terms of these slow roll parameters that will enter here. And as you can see, as I said, we have to take this total Hamiltonian as an operator, act on the wave functional, and set this equal to 0. So, and you can see already that this, inside these brackets, there are two main parts. So the first one is coming from the background Hamiltonian, the quantization of the background Hamiltonian, and second part comes from the quantization of the perturbation Hamiltonian. Yeah. Now, also to have this, so as I said, the quantized form was called a Wheeler-David equation. Also, to obtain this exact equation, because we had sum over all n, to get rid of that and to be able to obtain kind of solvable equations, we have used the following product ansatz. So we assume that these perturbation modes do not interact with each other. So we have, we can kind of write this, the total wave functional as the wave functional of the background part, which depends only on background part, and times this perturbation part, which is functional of also this perturbation gauge invariant variable, and we can separate all these modes and write it as a product. And substituting this here, we obtain the Wheeler-David equation for each mode separately. And now this omega n square eta, as I said in the beginning, that it was function of this functions of un and wn. So after using this slow roll approximation, it can get a more simpler form like this. So, and it is also given by these slow roll parameters at epsilon and delta, as you can see. And in addition, you can notice that this k also enters, which is coming from the contributions of the curvature of the space-time. And again, if we take the large wavelength limit here, again, we can recover the relation obtained for the flat case. Okay, now because instead of directly trying to solve this Wheeler-David equation, we actually apply semi-classical approximation, which means we want to obtain the let's say the Schrödinger equation of this field of these perturbations, and then we get also in addition the quantum gravitational corrections. So the fact that we can use this approximation, this Born-Oppenheimer type of approximation, is based on the fact that we have this. So for this approximation, you need to have kind of a heavy part and the light part. So the heavy part is played by the background, and the perturbations are the light part. So basically, because of that, we can kind of obtain. I'll show that at the corresponding level, we can get that we have classical background, and these perturbations will be quantum, and we will obtain the Schrödinger equation of these perturbations that propagate on this classical background. Okay, so we use this WKB-like ansatz. So we write that this wave functional we give with this form. And to implement this Born-Oppenheimer approximation, we have to expand this in terms of Planck mass, like this. Yeah, now to be able to get this corresponding orders of the approximation, so what we do, we basically expand this, substitute it here, then substitute this into the Wheeler-David equation here, right? Then we gather the corresponding orders of the Planck mass and set them equal to 0. By doing that, at this level, mp to the 4, we get the following condition, that the derivation of S0 is independent of the perturbations, as expected, that the background spacetime is independent of the perturbations. At the next order, you can obtain, again, for this S0 function, you can obtain the Hamilton-Jacobi equation. And this is equivalent to the Friedmann equation. So we basically recover the equation of classical GR. Next, we have to discuss this order, and initially we obtained an equation for S1 function, as you can see here. But throughout the calculations, one can simplify it and bring to this form, which is the Schrödinger equation. But to do that, we have to, because as I said, there is no notion of time, we can define this WKB time like this. And as a result, we can rewrite this initial equation of S1 as a Schrödinger equation. And also it's logical, right? Because at this level, when we have classical background and this quantum perturbations on top of it, which is basically QFT in curved space-time, you have to have a notion of time, right? So we can see that it can be introduced in quantum gravity through this. So kind of these dynamical variables are the scale factor and the field. So you can actually define time in terms of these variables, these two dynamical variables. And yeah, so and at the next order, where we have this term, you can get equation for S2 function. And again, doing some calculations and simplification, one end up with this form. So you can see there is also this contribution on top of this. Yeah, and we have kind of another wave functional, or which is the wave functional for the quantum gravitational corrected Schrödinger equation. Also, one should note that there is this unitarity violating term, but it has been shown actually by Klaus Kiefer's former PhD student that by a proper definition of inner product, you can get rid of this. So this doesn't invalidate all our calculations. So it's just a matter of the definition of inner product. But for now, we will just ignore this term. Of course, at the end, if you take into account and redefine this inner product, it will change slightly the calculations, but the idea will be just the same. So for now, we are just going to ignore it. Sorry, before I move on, I remember there should be a break. Should I stop somewhere, or it's not necessary?
I suppose that's up to you. If you want a break, you're welcome to
I mean,
have
I'm
one.
not tired. I can continue
Oh,
if students don't complain. So yeah, and also,
does anybody in the audience want a break, or shall we continue?
Okay, then I can go.
Oh,
We also
okay.
don't have much to finish, so okay. Now, so now we obtain these two equations, Schrödinger equation and modified or quantum gravitational corrected Schrödinger equation, which we have to solve. So to solve them, we use Gaussian ansatz for both of them. So using this Gaussian ansatz for the uncorrected wave function, we get this more or less simple Schrödinger. The Schrödinger equation leads to this new equation. And similarly, for the corrected wave function, if we use this similar Gaussian ansatz, we'll end up with this equation. So basically, from this point on, we have to solve these two equations, which are necessary to obtain the power spectrum, and the form of which I'll show soon. One can show that this power spectrum is given by the following expression. So you can see the real part of this omega n0 enters here, and the difference from the flat case is that there is this k entering. So for the flat case, you have just n cubed. Yeah. Now solving the Schrödinger equation and substituting the real part here, you obtain this well, complicated looking form. Now to try to make sense out of it, I present a plot to see what we obtained actually. Yeah. So as I said, we have to obtain this. The most important thing is to obtain the power spectrum of these curvature perturbations. Because this is actually what is related to this angular spectrum, which is the temperature anisotropies. So from the relation of this theta PST and phi and tilde, actually you can obtain the following. And now to see what actually is our result compared to the flat case. So this dashed line corresponds to the flat case, and this thick line is for the closed case. So to be able to plot it, I have fixed certain values for epsilon and delta. Of course, it should be reasonable. Those are very small variables, but one can clearly see that, as expected, because of the finiteness of the closed universe, there is significant suppression of the power. Actually, also seen in this Planck data, and also here there is a final cut because of the finite radius of the universe. Of course, this is not the final point. To be able to really fit the data with this Planck plot that you saw, we also have to calculate this angular power spectrum. Angular power spectrum is given by this form. As you see, this p theta is entering here, and these are some transfer functions, and this is impossible to do by hand. You have to use some codes to run this, to be able to obtain this angular spectrum and feed with the data to see how good it is. But what we can do at this point analytically is the following. So the Planck data is actually analyzed based on power law approximation. So this is quite consistent with the observations. So which basically means that this scale dependence is so insignificant that you can have this kind of spectral index entering here to describe this scale dependence. But the point is, because if you see carefully in our form, we actually have already explicit scale dependence. As a result, of course, you don't expect that this power law approximation is valid, because this is based on the assumption that the scale dependence is insignificant. And if we calculate directly, we will see that indeed, this because of the significant scale dependence, at least for large scales, where the main deviation from the flat model occurs, this power law approximation is not applicable. So there is this code called CMB fast, for example, that you have to use to feed the data based on your model that you are discussing to the actual observational data, is already based on this assumption entering here. So which means we have to use some more sophisticated numerical tools where this power law approximation is not assumed with the observations. Yeah, and also because, as I said already, Planck data is analyzed based on this assumption, it is kind of already restricted since the beginning. You assume that your universe, of course, should be scale independent. In that sense, I think one has to really, I mean, if you do that, actually, where if you have actually a finite universe, for example, of course, in that sense, it will look disfavored at the end of your analysis, right? Because initially you already assume this, and the main deviation of scale of this model, closed model, to the flat case is occurring for the large scales, and the large scales is where you saw this lack of amplitude in the spectrum. So one really has to take this very seriously. Now, the next goal of this work was to calculate also the corrections coming from quantum gravity. And you can see that the corrected power spectrum is given by this form, which can be rewritten as follows. Again, complicated looking, but to see again if we are in a right track, we can again take the large wavelength limit, and we can see that we again recovered the result that was obtained by Kiefer and his students for the flat case. And unfortunately, and also as one could also expect, this contribution, which is here coming from quantum gravitations, is actually very, very small, 10 to the minus 10. So also, I'll go back at the end to show you that because of the cosmic variance, the issue of cosmic variance, the error bars are very huge at this, to be able to observe these tiny contributions. So of course, it is nice to see that you can start from a quantum theory and get an estimate of the contribution. If it was possible, for example, to observe this, if one could calculate this kind of contributions from, let's say, different approaches of quantum gravities, one could also compare the results and also see which one is more consistent with the data. But unfortunately, because of the smallness of this contribution, we cannot really hope to observe this in the future. Okay, so this was it. Let me conclude. Okay, so I briefly discussed the different approaches to quantum gravity, introduced why we want to quantize it. Then we discussed how the canonical quantum gravity is formulated, and we particularly applied it for this inflationary universe and applied the semi-classical Born-Oppenheimer type of approximation. And we recovered this uncorrected and quantum gravitationally corrected power spectra. As I pointed out, the angular power spectrum can only be calculated by sophisticated numerical methods. By employing the closed model, one might be able to explain the observed lack of power for large scales. And finally, due to the smallness of quantum gravitational corrections to the power spectrum, we do not expect to confirm them by observations. Yeah, so this was all I wanted to tell you. Thanks for attention.
Well, thank you for the very nice talk. Are there any questions?
I have a question. So first of all, thank you for the very nice and very clear presentation. I really enjoyed it. And my question is very basic, I think, because it's been some time since I've last studied these cosmological models. But if the universe has positive curvature, then it's closed like a ball, right? So it hasn't a boundary. It doesn't have a boundary. It closes in on itself, right?
Also, one more thing I have to point out. Of course, in our case, we are discussing spherical universe, but in general, closed universe doesn't mean spherical. You can have different topologies. It can be torus, etc. So yeah.
Okay.
Yeah.
But it doesn't have an actual
no,
boundary,
there is no
right?
actual boundary. No.
Okay.
No. Yeah, but so which is why, for example, this kind of observations from CMB, etc., is nice, because based on that, maybe you can find out whether the universe is closed or not, because all our observations, wherever we look, because it's kind of zoomed out, right? You see only a very small section of the universe. So if it is a closed universe and it is huge, you are going to see locally flat universe, of course. So
right.
And maybe I go back to this Planck plot. Yeah, so as you can see, unfortunately, this cosmic variance causes these very large error bars here, where this significant effects for this finiteness could be detectable. It makes it very difficult, even if you, for example, as I said, if after the calculating this angular power spectrum and fitting it here and showing, exactly, you see that there is suppression. But again, anyone can say, okay, but there are huge error bars. You can't really prove that is the case. But for example, as I said, from this paper and this author, actually, I talked to her a few days ago. They kind of indirectly show that because there are some tensions in Planck data, you can show already from that there should be, for example, closed model is more favored. So it's kind of indirectly showing it should be favored. So of course, additionally, if we calculate this part and fit it to the data, in addition, it could show that, yeah, maybe we should take this really seriously. But again, as I said, these error bars are making the life very difficult. Yeah. I don't know, maybe at some point, technically we'll be able to get some type of observations that can help us to go beyond this this region where the curvature can really be significant and seen somehow.
Yeah, about that, again, this isn't my field, so please correct me if I say something
feel
wrong.
free to ask anything. So,
but unless as far as I know, the neutrinos decouple a lot earlier than the photons, right? So if we were to get a CMB-like picture of the neutrino background, then that could be a very good thing for this discussion, right?
Yeah, that's true. And also, for example, if there were primordial black holes and we could have the gravitational waves coming from them, those also could help us. But yeah, those are technically very difficult to do. And yeah, with neutrinos, usually everything is very complicated. But yeah, that's the hope. Yeah, you are right, totally.
Right, thanks.
I want to ask something.
Sure.
Thank you for the talk. Very interesting. So you just mentioned that different shapes of the universe could yield different effects. No, that could explain that beginning. So can you just say how would it change? Because you said you were using spherical symmetries. So what would happen if you have other types of geometries?
Okay, you meant the topologies if are different, or?
Yes, sorry, topologies.
Okay, yeah, actually, I don't know if anyone has calculated, but I assume there should be perhaps some differences in here if they take into account these different topologies. I haven't checked if there's this kind of calculations, but if I'm not mistaken, if you have these very complicated and different types of topologies, for example, you can see multiple pictures of the same star, for example, if you look to the sky. So this kind of topologies have some effects that definitely can result to this kind of issues, to have, for example, as I said, these different pictures of the same object. Yeah, but I can't really comment how it will affect to the power spectrum, to be honest. Yeah, I don't know if anyone has considered this, because usually even this inflationary scenarios, as I mentioned in literature, they just start with flatness, k equal to exact 0, and nobody really goes into this direction to discuss curvature and contributions, because, as I said, because inflation leads to the exponential expansion, and you can kind of argue that, okay, the curvature terms are not really significant, but the calculations that I showed, yeah, actually, okay, those are maybe not significant, and our universe now looks quite flat, but the power spectrum is different, right? So there is this suppression. So still, if this contribution is insignificant, but you can still have this effect even in the power spectrum. Yeah.
Great, thank you.
Sure.
Hi, Tatevik. Maybe
Hi.
maybe I can ask you something also. So you derived these quantum gravitational corrections to the Schrödinger equation, right?
Mm-hmm.
Yeah, exactly. So I wanted to ask you if this is so if this is also relativistic, because you know that the Schrödinger equation is not relativistic, right? So I wanted to ask if at the end you also have some, where is the, because I also don't see the, which is I don't see if it is manifest Lorentz covariant or so, right? So
okay.
I mean, is it relativistic or?
So the point is, this is not Schrödinger equation in quantum mechanics, but is the Schrödinger equation in quantum field theory. So where is it? Yeah. So this okay, I haven't written it explicitly, but this psi n0 is function of phi tilde, okay, or phi n tilde. So you are working in quantum field theory, okay, and showing a picture of QFT. So we are in a relativistic limit. Yeah.
Okay. Thank you.
Sure.
Yeah, I have a question. So when you are how you are promoting 3R, the spatial curvature two operators?
Sorry, I cannot clearly hear you. Can you repeat?
So there will be a term, means some first terms are differential terms and second term is 3R term, in Wheeler-DeWitt equation, where you have 3R minus 2 lambda You have derived the Wheeler-DeWitt equation. I mean, exact
okay, you mean,
Wheeler-DeWitt equation
let
in
me,
terms of
uh-huh.
Hij. Yeah, this
Yeah,
equation.
here. Mhm.
So when you are promoting this to operator, 3R should be some kind of operator, huh? So that you can act it on the wave function.
Yeah. So as I said, you have to take this Hij as an operator, and particularly in our case, Hij is given by the scale factor, right? So basically, you take the scale factor as an operator. As a result, everything that is function of it becomes an operator.
But 3R will contain the partial derivative of these Hij's with respect to means the partial derivative of this derivative of this Hij with respect to coordinates, all the coordinates, isn't it? Means how will you deal with that coordinates?
Let me go back. I think I have some exact forms for this. Oh no, I don't have. But I think so. You see, this R is related to this. So those are related to the momentum, right, of the Hij. So the rule to quantize it. So you take the scale factor, for example, in this case, as an operator. I have to go back again. Sorry. Okay, so it will act like this, and the quantities that are related to the momentum will act on the wave functional like this. So if your quantity contains this this term, the momentum are given in terms of this momentum, then it will act like this. I hope I am answering your question.
No, I'm saying the three here our Hij will be A only, huh?
Will be what? Sorry.
Means this Hij means it is here A only, huh? Scale factor.
Yeah, so Hij in our case for Robertson-Walker metric is given by this. So this becomes an operator. So in your Hamiltonian form, there will be entering this A, and there will be entering the momentum of A. So
means del by del A, huh?
Yeah. So let me go here.
But in 3R there will be a derivative of means A itself with respect to the coordinates whichever there is in ds squared.
Okay. Yeah, but I mean, after the calculating the derivative, you can always take an operator on it, right?
There will be a derivative of A with respect to the time and this with respect to not with respect to
no,
time.
that's the point. That's the point I'm making. If you have a derivative of A with respect to time, you can express it in terms of the canonical momentum. And in this equation already, you see this canonical momentum, the operator becomes like this, the del squared del A alpha square. So yeah, and let me show. So you see this P alpha is defined like this. So there is this A dot that you are talking about is entering here. So when you quantize this, you take this as an operator, and you have to express your derivative, the derivatives of this momentum in terms of the momentum, because we are working in Hamiltonian formalism, and then only you can take an. Sorry.
Yeah, should I ask? D omega square, means this D omega square will contain theta phi r x y z. Huh?
Yeah.
So there will be in 3R there will be a derivative with respect to x y z also.
Yeah.
Of A. How you promote this to operator?
Yeah, I mean, if I don't remember the exact forms, but I understand that you should just calculate the derivatives, and after that only you take an operator. So the point is, if you have only for the case of partial derivative with respect to time, you have to express this in terms of momentum and only quantize, but the other derivatives won't affect. So you just have the A as an operator, that's it.
So can I ask one more thing?
Yeah, sure.
Suppose there is H phi term also in the Hamiltonian. You are considering matter also.
Sorry, again?
In the means Wheeler-DeWitt Hamilton, whatever Hamiltonian we are getting, suppose there is H phi also, means matter Hamiltonian.
H what?
I am saying you are adding matter also in the Hamiltonian.
Yeah, exactly. So here you have the contribution of Hj and the matter part.
So now the question is this: H phi will contain phi dot as well as Laplacian of phi.
Yeah. So, and
Now-
this phi dot is related to this p phi, the momentum. So you have to have only two things in your Hamiltonian. So from the Lagrangian, in Lagrangian, just from classical mechanics, you have the coordinate and this derivative, right? In Hamiltonian formalism, you have the coordinate and this momentum. You are not, let's say, allowed to talk about these derivatives. Everything should be expressed in terms of
Yeah,
those, right? So
yeah,
that's the
no-
point. So,
Now,
so here,
momentum you can promote to operators. Huh?
yes.
But what will you do with Laplacian of phi? How can you promote that to a momentum? Laplacian of phi, time, momentum is defined with respect to time. But
But
what will,
why, sorry, but why are you considering Laplacian? We are working with Hamiltonian formalism. All this quantization procedure is based on Hamiltonian formalism.
but H5 will contain, H5 will contain, what is that, phi dot also?
No,
And-
H phi doesn't contain, that's the point. In Hamiltonian formalism, you don't have phi dot. You don't talk about phi dot. You have the momentum, P phi. So as I said, in Lagrangian, you have this coordinate and its derivative. In Hamiltonian formalism, you have the coordinate and this momentum. You are not allowed to even talk about how it is related to the this Lagrangian form. So you are working with these variables only. That's it.
There,
So
there will be a partial derivative of phi with respect to x, y, z also in Hamiltonian.
well, here you see there is only this term entering here. I don't understand which model are you considering.
No, no, I am interested in. I am asking this. So there will be a term. There will be two terms. So suppose I am talking about how to go from this Lagrangian to Hamiltonian. Huh? Phi
Okay.
dot will be there. You can promote phi dot to momentum. Phi dot is just
Yes.
but there will be a gradient of phi there in Lagrangian.
Okay, let's say if you have, okay, but what?
So-
I mean, you are not working with, you are not quantizing your Lagrangian, you're quantizing your Hamiltonian.
I have another short question.
Sure.
Back in the beginning, when you said that the constraints they separate into what you call the Hamiltonian constraint and the diffeomorphism constraint, right?
Yes.
So my question is, you said that they're first class, and
No,
I believe they both.
You are mixing two things. So here you obtain these two constraints. This is coming from the variation with respect to the lapse, and this one is coming to from the variation with respect to the ship. The first the first class constraints were these that we obtained. So just don't mix with this. So basically, the constraint that I was talking about were imagine like this. So those are additional first order Hamiltonian constraints that are related to these perturbations that you are adding. So those are two different things.
Right. But and sorry, I keep mixing up first order and first class. But the ones you showed before, the Hamiltonian and the diffeomorphism constraints, they're or are they first class in the sense that do they correspond to gauge to gauge symmetries? Because I'm used to thinking about this about these constraints are just following from diffeomorphism and variance. So that's a gauge symmetry, right? If your theory.
Yeah. So basically, this is what it describes. Yeah. Yeah. But I'm not sure if we can just specify them as first class constraints. I haven't thought about it.
Right.
Yeah.
I was
Okay,
wondering
thanks. I think
what kind of transformation do they correspond to, but I don't. Maybe it's not this this clear.
Yeah. I'm not sure about that.
Okay. Thank you.
Yeah.
Are there any more questions from anyone in the audience? If not, let's thank the speaker again.
Thank you.
Thanks.